Okay, game on. I just spent the last 45-ish minutes, 35 minutes going through the rest of Module 2 because what you have to understand is we plan, but I don't just get up here and I'm like, okay, I know exactly what to teach. I need to know what Engage New York wants me to teach. So I spent, again, the last 45 minutes, maybe an hour, going through lessons 12 through 20, making sure that I knew exactly what they wanted so that I could give you the best information. Am I still going to ad-lib and make it Mr. H's? Yeah, I think that I'm pretty awesome. Therefore, I'm going to make it how I want to. But it's going to be pretty good. So, two numerical values. We're looking at an x and y. We're looking at an ordered pair. We're going to be doing all of this. The key to this lesson is telling me whether something, a set of data, even though a set of data isn't always going to be exact. So we've learned already that data can kind of have this ebb and flow type thing. Scientists use scatter plots quite a bit to see what the data is doing. It would help if I had my keyboard. I was all ready and prepared, ready to crush the day, starting on lesson 12. I'm making videos 12, 13, 14, 15, 16, and then 19. That's my goal today. Okay, so you have this huge chart of 14 cities. Elevation above the sea level is X. Y is the number of clear days. You've got cloudy days. You've got other cloudy days. I don't care because I'm only concerned about my X and my Y. So here are our cities. Here is the sea level. Here are the number of days. So when I take a look at this, the goal that we want to make today is saying, okay, what appears to be happening? As the elevation grows, as my X values get bigger, what's happening to my Y values? Is there a consistent pattern? That's what we're looking for in scatter plots. So right now, as my X values get bigger, it appears that my Y values are getting bigger. If both X and Y increase, we say that this has a positive correlation, because we can make a line of best fit. And we're just guessing at this point. We can make a line that's going through these points that says, okay, Mr. H, I can kind of see how you have that line going. Are they all on that line? No. But do I have most above, most below? Yeah, that's a pretty good line of best fit. Notice how the line is going up. If our scatter plot has a positive correlation, positive again meaning my X values increase and my Y values increase, then our slope of our best fit line will be positive. That's the key to this, is do we have a correlation? In this case, this is linear. We want to know, can it be linear? And again, in this one, it's absolutely linear. Okay, so there's a linear relationship. Does it have to be linear? No. So here's three others. Let's take a look at 1 and 2. So once again, as X increases, Y appears to be increasing. Can I make a line of best fit? Well, kind of, yes. Does my line appear to be going up? Yes. This is called a positive correlation. Same idea here. Can I make a line of best fit? Again, yes. In scatter plot 2, as X increases, Y decreases. Listen again. As X increases, Y decreases. So we've got one positive, one negative. Increases positive, decreases negative. Therefore, this is a negative correlation. Both are still linear. As we look at scatter plot 3, this is all over the place. I can't make a line that's gonna get all of this. If we just have it scattered and there is no correlation happening, we say there's no correlation. It's not positive, it's not negative. We don't know. There is no correlation. Okay? So again, we've got positive correlation, which means it's tending to go up. This was a linear positive correlation. This was a linear negative correlation. Does it have to be linear? Again, no. Not every relationship is linear. Okay? Well, scatter plot 1. This to me appears to be linear. I can say, okay. There's my lines. It's a negative linear correlation. I like that one. Okay? No problems. I can say, yeah, there's a relationship. Appears to be linear. Not only is it linear, but it's negative. Well, let's take a look at this one. Okay. Is there a relationship? Well, yeah, it's going down. Is it linear? Absolutely not. This is called an exponential. And we're going to talk more about that in lesson 13. But is it linear? Nope, 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 nope. That has a negative downward sloping exponential. Again, we'll talk more about that in the next lesson. But does it have a relationship? Yeah. Can we make a 9 a best fit? Yeah, except it's not a line. Okay? But it does have a relationship. As x increases, y is absolutely decreasing. And that's how I would say that. And is there a relationship here? So once again, as I take a look at this, they're all over the place. I can't make a good positive, a good negative. There is no relationship. There is no correlation. So the keys to lesson 12. Scatter plots are going to be from now until the end of the module. This is going to be a huge portion of your test. Positive correlation, x increases, y increases. Negative correlation, x increases, y decreases. Linear correlation, we can make that line, both positive, both negative. And we're going to learn about exponentials, and we're going to learn about quadratics here in the next lesson. So this was a short video. Again, scatter plots all over the place. No correlation, positive correlation, negative correlation. Let's get to lesson 13. Okay, let's rehash. So in lesson 12, we talked about correlations of scatter plots. We said, could it be linear? Which means it's forming this line. Sure. Even though there's points all over the place, we know that there could possibly be a line of best fit that could be linear. But does it have to be? No. There's a lot of situations in the real world where things don't always go straight up. They don't always go straight down. They ebb and flow. They might have some humps to it, okay? The perfect example would be, let's shoot off a bottle rocket. It goes up. It doesn't keep going up. It's got to come back down. So as we shoot it up, its speed increases, but it's decreasing, it's decreasing, and then it hits the peak. And then what happens? The speed increases as it falls to the ground. If we shoot off 20 bottle rockets, are they all going to have the same curve? Maybe, maybe not. So that would be something of a quadratic. Well, Mr. H, what do you mean quadratic? So we're still talking about two numerical values, but now we're talking about some different things. So if we have a curve that looks like a U, this is a quadratic function. Quadratic meaning that if we had an equation, instead of just having x, it would be x to the second power, okay? X squared. And we will talk about quadratics, I want to say in module 4 or module 5. I don't really remember, but that's a big portion of our second semester. So this is a quadratic. Well, what other types are there? Well, in lesson 12, I taught you a little bit, and I didn't teach you. I showed you about an exponential. An exponential means that it will, forever and ever and ever, it might hit here and go up, and it's going to go down, 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 but it will never hit zero. It's exponentially growing. In this case, it's exponentially decaying. If I have this one, an upward slope would look like this. Okay? Exponentials don't have the other half of the u. So the difference between the quadratic, an equation that might look like y equals x squared, versus an exponential is going to have the x as a variable or as an exponent. So it might say 3x. This one might be, I don't know, 3 to the negative x. Okay? So those are exponentials, where our variable is an exponent. And that makes sense. Exponential, exponent with our variable. So you can have an upward sloping exponential function. You can have a downward sloping exponential function. How are we going to tell in the graphs? Well, listen, you guys are smart cookies. You can do this. So we're going to really consider these four. Let's see if I can make it just a little bit smaller. There we go. Okay, so we can take a look. You should be able to look at all of these and say, okay, do I have some type of, I guess, what's the word I'm looking for? And I've just forgotten my word. Oh my goodness. Do I have some type of pattern? Okay. In scatter plot 1, we can say absolutely. We absolutely have some type of pattern because there's a relationship. There's the word I'm looking for, a relationship. This relationship is most of these points as x increases, y decreases. Does it appear to be linear? Yeah, for the most part, those points are staying right around that line. This is a linear pattern that has a negative correlation. Okay, number 2. Well, we can clearly see that as x increases, y is decreasing. That's fine, but we can't make a line of it. Well, can I draw some line of best fit that appears? Sure. So what's happening there? Oh, this is an exponential with a downward trend. It's trending down. Okay. How about scatter plot 3? If I take a look at scatter plot 3, it is absolutely scattered. There is nothing that I can say about this besides it is absolutely scattered. Scatter plot 4. Ooh. Okay, well, this is the easy part. This is going here. Oh, but look. We've got one more like this. So if I've got this U shape, that is called a quadratic function. Quadratic function. That is muy importante. A linear, an exponential, a quadratic. They all have relationships. Okay? So how do we use these exponentials? How do we use these quadratics? And that's a fair question. So there's our linear. We can use that. I'm going to skip that one because I want to go to this one. Okay. So a farmer sometimes uses fertilizers to increase crop yield. What that means is they're going to get more crops, but often wonder just how much fertilizer they should use. The data shown in the scatter plot below, blah, 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 blah. Okay. The researchers who conducted this study decided to use a quadratic curve. Well, why? Because, I mean, it's literally following a quadratic. We start here, and it's going down. Is there a peak to my quadratic? Is there a high point before it starts coming down? Well, yeah, something there right around here. I'll say, my line's a little crooked, I'll say this is about 225. 225 what? Kilograms. Okay, so what it appears, and here's how I'm going to interpret this graph. It appears that 225 kilograms per 10,000 square meters gives me the most yield. This gives me the most yield. Anything lower than that doesn't give me as high of a yield. And anything more than that, it starts to curve back down. So using more fertilizer doesn't actually help. It's actually letting my crops not get as big. It's not giving me as much. So that's why we're using these graphs. Now, can we be more specific? I bet we can. Let's take a look. Okay, so They've given us this equation. This is the equation for that scatter plot. And you're going to learn about how to make these equations in a little bit. Y equals 4 7/10 plus 5/100 x minus 1, 2, 3, 1 x squared. Okay. They want us to fill in this chart. Okay. So if I substitute 0 in for my x, that leaves me with 4 7/10. If I substitute 100 in for my x, that should leave me with 8 7/10. And you might say, Mr. H, how do I substitute it in? Literally plug it into your calculator and do exactly what it says. If you have trouble with that, let me know and I'll gladly help you. But most of you don't have the fancy dancy is what I was going to say, the fancy super duper calculators. I don't even know where mine is. There it is. Then the next one, these two give me 10 7/10. Huh, that's weird. And then when I substitute in 400, it gives me 8 7/10. So does that make sense? Let's go back real quick to my graph. Does it make sense that at some point this side and this side are the same, but then as you get more fertilizer, it goes down? Yeah, because remember, there's a peak up here. Quadratics either have a peak or a valley. This peak is the maximum number of fertilizer kilograms that we want to use. But you need to know how to substitute it in. So based on the quadratic, what would you recommend a farmer use? About 225 kilograms, because that's the peak of that quadratic. Understanding how to work with these is important. Okay? So let's go to the lesson summary real quick. Maybe. There it is. So here's what you need to know from 12 and 13. A scatter plot can be used to find whether there is a relationship. It could be linear, but it doesn't have to be. Linear, quadratic, exponential, those are all types of functions that you will absolutely see in the real world. COVID is an exponential function. We don't know what the max number of cases could be. Linear, how much I get paid each week. Quadratic, again, that bottle rocket going around. Models can be used to answer questions about how two variables are related. We're going to really dive into that. So we've done lesson 12 with scatter plots. We've done lesson 13 with scatter plots. Let's keep using scatter plots, folks. Maybe. Bye. Yo, hope you guys are doing well. It's still November 13th. I am on video number 4 for the day. I feel like I'm crushing life. It's 10:15 in the morning. We had a meeting until 8:30. I made video 9. It took me about 10, 12 minutes. I told you I spent 45 minutes getting ready. Now we get to start playing with the calculator. So I'm not sure how this is going to go on the video. So if this needs to be retaught in class, which I'm sure it will because you don't have these calculators at home, what I'll suggest right now is making sure that when I start using the calculator and holding it up and showing you, you actually write down steps. Step 1, I press. Step 2, I press. Fair enough? Fair enough. We are in, maybe, we are in lesson 14. Now we are modeling relationships with a line. So if you've noticed, I've kind of jumped the gun and I started making those lines of best fit on your graphs already. You should have seen in all of the videos with the scatter plots where I'm kind of already done the line, okay? Today, we are going to find out the exact line of best fit, and we call it a linear regression. So looking at this, you should be able to say, hey, this appears to be positive. This is a positive, and it appears to be a linear regression. This line appears, or these data points, appear to be positive. Okay? That's not hard to see. Investigate this and say, okay, well, how do we know? Because as the shoe length gets bigger, the height should get bigger. Fair enough. So what do we truly want to do? Well, we want to be able to use these data tables, these coordinate grids, And we want to say, okay, what can we do with this? Well, let's find out. Is there a relationship? Yes. How would you describe the relationship? Linear. Do the men with longer shoe lengths tend to be taller? Yeah. Well, that's great. That's an easy one. Okay. But here's the same graph with two different models. Why is blue better than the black? Well, again, hopefully at this point, I've kind of talked about it and you can understand. X is increasing, so is Y. So it's not going to be a negative correlation. It should be positive. Even though this goes through 2 points and this doesn't go through any, we're still pretty pleased with it being a positive correlation. That's something important to know. One of the men has a shoe length of 11 and 8 inches and a height of 71 inches. Circle the point in the scatter plot in exercise 3 that represents this man. So 11.8 and 71. So let's go back here. 11.8, right around here, and 71. Okay? Why do they have me do that? Don't know yet. Let's find out. But knowing how to be able to find those on the graph is important. That's how we're going to interpret this, because you need to. Suppose that you do not know this man's height, but you do know that the shoe length is 30 inches. If you use the model this, what would you predict his height to be? Okay, so I have y equals 25 and 3/10 plus 3 and 66 times 11 and 8/10. Well, why am I substituting that in? Because my x, which is my shoe length, is my x. 11 and 8/10 times 3 and 66/100 plus 25.3 gives me a height of 68.488, which I'm going to round to 68.49 inches. If you use the model, what would you predict his height to be? Well, let's try here. 130 minus 5 times 11 and 8/10. Y equals 130 minus 5 times 11 and 8/10 gives me 71 inches. Which model was closer? Well, the second one. Is that model a better fit for the data? Is that model a better fit for the data? Why or why not? So this is a tough question. Notice these are actually slope-intercept form. Even though the x is not closest, I want it to be close. So y equals 3 and 66/100 x plus 25 and 3/10. Y equals negative 5x plus 130. Why is this, even though it gave me 71, not the better choice? The key is the slope. We've already said that this is a positive linear relationship. If it's positive, my slope has to be positive. This has the line going downhill. We know that it's not a negative slope. This is a negative relationship. So is this the better choice? Absolutely not. Even though it's closer for that particular one, this line, this equation will be better for all. Okay? So it's important to know, hey, it's linear. Is it a positive or a negative relationship? Moving on. Okay, so we're still, residuals. I would make sure that you have this written down. I would make sure that you have this somewhere written down. We will be spending the next 2 or 3 lessons talking about residuals. Residuals can be both positive and negative. They're like our deviations, okay? The deviation's how far away from the center. Well, in this case, our center is the line of best fit. Our residual is telling me, is it above, positive, or is it below that line of best fit? In this case, okay, we predicted 71 and 42/100 of an inch. And you can read this and say, okay, his actual height was 74. So we take 74 minus 71 and 42/100. We're off by 2 and 58/100 of an inch. We can find all of the residual values of everything if we know the actual and what we have based off of our heights. And we'll probably do a little example with this, with our own shoes and our height. So here's what happened. I'm not going to do them all. I'm going to do a couple. Just by looking at this residual, we know this is positive because his real height was bigger than the line. This one's negative because this is 65. We don't know what the predicted is yet until we substitute it in, but I can guarantee the predicted is going to be bigger than 65. So what do? We get our calculator. We do 25 and 3/10 plus 3 and 66/100 times 11 and 8/10. And it gives me 68 and 488. I'm going to go 68 and 49. That's how I'm getting my -3 and 49/100. Okay? So the key with residuals is the actual height or the actual value minus the predicted. Where do we get the predicted? We get the predicted by substituting in to the equation. We get the predicted by substituting into that equation. Because remember, maybe, we know that this line is the best line for all of these points. But notice how none of the points are actually on that. Some of them are above it, which means it has a positive residual value. Some are below, which means it has a negative residual value. Residual is the actual minus predicted. Okay, so we're not going to complete all that. If the residuals tend to be small, if the residuals are between 1 and 2, what does that tell me? Well, that tells me all of those points are close to my line. The closer the residuals are, the better my data is. It's just like that deviation. The closer that deviation was to the mean, that means the center of the data is all right there. If we've got residuals that are like 35 and -27, they're really far away. Those are outliers. We want all of our points to be somewhat close to that line. So the most common choice for best line is squared residuals. And it's going to go into all of this kind of stuff. But let's talk about how we're going to make a residual line from our calculator. So let's go back up all the way to our data here. This was the data given to me, the x values and the y values. I'm going to show you how they got their equation. So I'm going to try to do this without screwing things up. Here's my calculator. The first thing that I'm going to do is I need to enter that data. I enter that data by pressing the stat button. So step 1, press stat. I'm now at edit calc tests. To enter that, I press edit. Step 2, press edit. Notice how I already have these in there? Well, I want to show you how I'm going to do that. I highlight L1, I clear it. I press down, I highlight L2, I press clear. I go back to L1. To enter these in, I physically enter in my numbers. So I'm not going to show you this. I put 12.6, enter. 11 and 8/10, enter. 12 and 2/10, enter. I'm going to stop saying that now because I'm going to screw myself up as I'm doing it. But I'm entering in all of my x values first. There's my last x value, 11 and 8/10. Notice how it says L1 and in parentheses it says 10. That's the number of data points. I press enter and it says L1 11. There's nothing there. Now I go to L2 and I enter in all of my L2. 74, 65, 71, 67, 69, 68, 70, 69, 72, 71. Notice how all of my data matches up at the bottom, 11 and 8/10 and 71. If I had an extra number down here in my x and not my y, I did something wrong. Okay, I don't know how well you can see that, but there's my numbers. So now we need to find the line. To find the line, I press stat again. We want to go over to calculate. Okay, we do have linreg right here. This is a linear regression that says ax plus b. I want you to get into the habit of just scrolling down or pressing 4. It says X list, Y list, frequency list, store. I want you to keep pressing enter until it gives you numbers. We're only concerned right now about the A and B because Y equals AX plus B. Notice AX is 3 and 6/10 X plus B, which is 25.27, which they round to 3. Let's see how close we are. They told us the equation was 25.3 and 3.66. So let's take a look again. 3.657, oh, they round that to the 100th. 25.3, oh man, We have the same exact equation that they do. So one more time, how do I do this? To get my line of best fit, my linear regression, I press Stat. Edit's highlighted, I press Edit. I enter in all of my numbers. To clear out one of those, I highlight L1 and then I press Clear. I'm not going to do that. Once I've entered them all in, I press Stat. I move my right arrow over to Calculate. I want number 4, linear regression AX plus B. Y equals MX plus B? Absolutely. I press 4. I press Enter until I come to this. Y equals AX plus B. We're going to deal with R in a little bit. That's the correlation coefficient, but we're not there yet. Okay? So I will help you if you need help with the calculators when you come in. This is linear regression, line of best fit, which we absolutely will be using. Okay, so we are on lesson 15, interpreting residuals from a line. Again, residuals are going to tell me whether my line of best fit is a good choice. And it's also going to tell me, hey, you might not have enough data, but it's not just going to be a linear line. Even though it looks right now like it's linear, it might be a quadratic, it might be an exponential. And we use residuals to find that out. So the first thing we have here is calculating predicting errors. Yeah, right. So the gestation time for an animal is the typical duration between conception and birth. So the longevity of an animal is the typical lifespan for that animal. Okay? So you've got the gestation, how long the mom is building that baby, to how long the years are. Okay? There's 13 different types here. We are able to make a scatter plot. There it is. Does there appear to be a relationship here? I would venture a guess and say, yes, there is a positive relationship. The longer the gestation period, the longer that animal lives. Okay? So it's positive. Could it be linear? I would again say yes. There is a positive linear relationship happening. So they substituted into a calculator all of those numbers. So they did stat. They cleared out L1, L2. They entered them in, and they ended up with this as their equation. Okay? The least square lines, the linear regression, has been added to the scatter plot. So this is the line of best fit according to the calculator. Still, so far, so good. It says, suppose a typical animal has a gestation of 200 days. Approximately, what value does the line, and then it stops, so it would be helpful if I had my notes here, which I do. Let me put my coffee down. It says, suppose, approximately what does the line value predict for the longevity of the type of animal? So the line predicts at 200, I've got something like, I'll say 13. So 13 years for my guess for number 2. That's my guess. And it's, again, just a guess. Would the value you predicted in exercise 2 necessarily be the exact value for the longevity of that type of animal? Well, no. Could the actual longevity of that type of animal be longer than predicted? Sure, it could. Could it be shorter? Sure. It's a prediction. This is the line of best fit. If you notice, when we go back to this graph, there is not a single actual value on this line. These are predictions for all the animals. Based off of what we have, this is the best guess that scientists, in our case, mathematicians, came up with. But this is what scientists do. They use lines of best fit. So you can investigate this further by looking at types of animals included in the original. Okay, so we know the lion. Its gestation time is 100, and we know that it lives for about 15 years, which is right here. The least square lines is 10 and 6/10. So how close is it to being correctly? More precise, how do you have to add to 10.6 to get the lion's true longevity? So this is a vertical line regression model. Okay, this is a vertical line regression model. It's showing exactly how far from this line to the actual value it is. What if I drew the line down? Would I have a positive or negative? If you're saying, well, Mr. H, that's a dumb question, you're right, it's going to be negative. So if I have to draw that line down, you could have a vertical regression down. So let's continue to look at this. We're going to do a lot of this in class. Repeat this for the sheep. Okay. Again, it is important to know the residual is actual minus predicted. So our residual, and I think I called it wrong, I think I called it regression. The residual value of that one was positive 4 4/10. The baboon residual, its actual is 20. So how would I find the best fit? Well, I'd say 20 minus 5.9 on that line. It's going to give me 14.1. Okay? So it's showing me positive residuals. It's showing me negative residuals. But notice, it's not showing me a residual of like 17. If you predict something and the residual is off by like 17, it's probably not a good guess. And that's what it's saying right here. The predicted longevity is 17.4. Think about what the actual longevity of this animal might be. Could it be 30 years? Well, 30 minus 17.4 is like 12.6. Let's go back up to our residuals. Does 12.6 show up at all? Would that make sense? Well, no, that's too far away. Just like our deviation, it's too far away. So it's probably not going to be 30, and it's probably not going to be 5. So judging by the size of the residuals, what values do you think could be reasonable? Well, we're within 5 or 6. So I'd say, okay, let's subtract 6 from this. So it could be between like 11. Let's add 6 to that. And it could be to about like 23. Those are fair numbers. So between 11 and 23, that's much fairer than saying 30 and 5, based off of the residuals. So residuals are what's giving us the basis of our best guess. Okay? So when a least squares line is used, that's our linear regression line, its residual is actual minus the predicted. Residuals are the vertical distances away. You will use these to make guesses. And we're going to, again, use a couple things. I'm going to try to do some things in class where we make our own line of best fit, and we're going to use residual facts as well. The next one shows residuals that's going to help us tell whether it's going to be linear or nonlinear. Residuals are importante. Let's see. Have a good one. Welcome to the last video of Module 2. We have now made it through 2 modules. Count them, 2 modules. It's only sometime in December, maybe. I don't really know when this video is going to be. My guess is sometime before winter break. So we've made it through 2 whole modules in a semester. Huzzah! This should be an easy lesson because I have been preparing you for this the entire time. If you remember when I said, hey, I spent 45 minutes reviewing all of the material so I can make sure that I knew how to teach Engage New York, there's a reason. I like to throw in a little bit of extra stuff to make sure that we're building up to what they actually want, rather than just saying, okay, here it is, here it is, here it is, throwing something new at you. There's nothing new here. When you look at these graphs, you should be able to say, hey, Mr. H, there's a positive relationship, there's a negative relationship. I've already talked to you about correlation. There is a positive correlation here because as x increases, y appears to be increasing. There's a negative correlation. Why? Because as x increases, y decreases. You should be able to look at that, and there are no problems when you look at that. But what does that mean? Well, there are stronger and weaker correlations. So now let's look at these. Okay? So as I take a look at these 2 examples, would you say that there's positive or negative or any type of correlations happening? So as we look at these, what can we say about 3? Do you think it's positive? Do you think it's negative? Well, it's kind of all over the place. It might be positive. This one, though, man, that looks really good. That's a nice positive correlation. I'm not as sure about this one. This is where we talk about strengths of correlations, okay? Because there are better linear correlations. There's stronger ones, there's weaker ones. I would say this is a weak positive correlation, where here I'd say this is a nice strong correlation. And there's going to be a way to figure out whether it's true or not, whether it's strong or not. Let's move down. Okay. So we've got these 3. So we've got scatterplot 5, which appears to be positive, kind of. We've got scatterplot 6, that definitely appears to be positive. Scatterplot 7 is a strong, strong candidate. It looks rock solid. It looks amazing. It's a nice almost line. This is almost a line. Okay. So if I had to put these in order from strongest to weakest, definitely scatter plot 7, scatter plot 6, scatter plot 5. Not saying that scatter plot 5 isn't positive, but it just has the weakest correlation. So how can we figure that out? Well, which one here has a stronger? You know? I don't know. They're both pretty good about this one. So how are we going to figure that out? The strength of the linear relationship for these might be exactly the same. So we use what's called the correlation coefficient. The correlation coefficient states that R, which is what we're going to call the correlation, can be anywhere as low as -1 or as anywhere as high as +1. For strong relationships, we want a 1 or we want a -1. Negative correlation coefficient just tells me about the line, whether it's negative or positive. This is linear. I mean, I can draw a line through all of those points. We know exactly what the equation is, which is why my correlation coefficient is +1. That's as strong a positive correlation as possible. Here, it's 70/100ths. I can draw a line. It's saying, okay, it's somewhat close to 1, but not exactly 1. So it's not perfect, but it's still pretty strong. The farther we get away from 1 and -1, the weaker the correlation. Because I could put a line here, I could put a line here, I could even probably put a line here. But they're saying it's a positive correlation, so they're saying it's going up, but there's not a lot of good data there. Oh man, -0.1. This is about as far as we can get away from 1 as we want. It's negative, but it could be positive with an outlier. This isn't good correlation. This is weak. It's tough to say whether it's positive or negative. Oh, -0.32, -0.63. We're getting closer and closer to being strong. -1. This is linear. 1 and -1 are linear. So how do we find the correlations? Well, let's go to example 4. Which is our shoe lengths, which I believe I still have in my calculator. So I go to stat, I go to my list. I've still got my shoe lengths in there. So how do we find the correlation? Well, first off, we need to make sure that we've got everything in here correctly. We want to make sure that we've got everything turned on. So in your calculator, I want you to press second catalog. And then we're going to press this down arrow. And we're going to hold this down arrow for a while until we get to the D's. And we are looking for diagnostic on. When I get to diagnostic on, I'm going to press enter. I'm going to press enter and it says done. We need to make sure we do that. Because now when I go to stat and I calculate, and I'm going to go to my linear regulate, I press enter, it gives me not only my numbers, but my R value. It's saying that the correlation coefficient for the shoe sizes, as my shoes are bigger, my height's taller, it's saying that it's about 0.65. 0.65 is close-ish to 1. It's not a perfect 1, but it's close to 1. If you go to this table, which you have, it's telling me what we know. So 0.65, this is a moderate positive linear relationship. Not perfect, not horrible, but it's not like this. This is perfect. It's a linear relationship. Man, there's a really strong one. And it shows me where they would fall. Now, this is important. Just because there's a strong positive or strong negative relationship, that doesn't mean that X affects Y. Okay? They've done studies that have shown there are better readers, young kids who are better readers with bigger shoe sizes. So does that mean that shoe size tells me if you're going to be a better reader? No. What that says is they show a pattern. It doesn't necessarily mean that it's exact, but it shows a pattern. So X doesn't always affect Y the way that you would think it. For shoe size, I've got a big shoe. I've got a size 12. I'm 5'7". That doesn't really fit. Okay, so there are always reasons to say, does it affect things perfectly? No. Calories. So there's an example here that talks about food with sodium. Sodium has no calories, but the more sodium is in a food, it's saying the more calories are in the food. But why? Why could that be possible? Well, if you have more sodium, maybe you have more fat, maybe you have more carbs, I don't know. But there's other factors that affect it. Sodium just happens to be one that will balance out with it. So the correlation coefficient tells me how strong something is. Is it linear or not? So a correlation coefficient is going to really help me say whether, and here's what you're saying, there's not a cause and effect. I'm going to let you read this on your own. So if you want to pause, if you want to find it, there's a correlation coefficient there. But this is what I want. Linear relationships are often described in terms of strength and direction. Direction being positive, direction being negative. The correlation coefficient tells me whether it's a good linear relationship or not. The closer the positive one or negative one, the stronger it is. Listen, guys, we are done with Module 2. We've done a lot of linear stuff. I can't wait to move on. You have a test coming up.